Hello students, in last lecture I had started the topic kinematics and in this session also it will be continued. So without delaying much, let us start. We are going to interpret now some velocity time graphs. So velocity time graph. Let us draw a graph, take an example and then we can interpret it. On y-axis is velocity taken, and as I had said that on x-axis generally time is taken. So here also I am taking time along x-axis and velocity along y-axis. So let us see, my graph is like this. How is it interpreted? This is the origin. Let this be point A and this be point B. This is some time TA, this is some time TB. First I am going to write slope of this portion OA and then slope of this portion, let this be theta A, and then slope of this portion, let this be theta 2. Now what does this theta slope of first portion OA represent? Tan theta, if you write, tan theta 1 would be change in velocity, because slope is written as delta y upon delta x. So delta y would be velocity at A minus velocity at 0, because it had started with 0 velocity. So 0 upon the time taken, which is equal to TA minus 0. This is how tan theta 1 can be written. And as you know, this is velocity upon time term, so it has to be acceleration. So this is acceleration for the part OA. Now let us come to part AB. So here again, if you write tan theta 2, slope of this part, it would be equal to change in velocity, that is velocity at B minus velocity at A upon the time span. Now what is time span for the part AB? This is from TA to TB. So in denominator it would be TB minus TA. Again this is change in velocity upon time. So as according to definition of acceleration, this will be acceleration for the part AB. Let this be A2. Now if you interpret the values of A1 and A2, as you can see here, theta 2 is more than theta 1. So theta 2 is more than theta 1. Of course we can say tan theta 2 would be more than tan theta 1, or we can say this as well, that A2 would be A1. What kind of motion this predict? This is acceleration from A to B is more than acceleration from O to A. Now more acceleration does mean that velocity is changing at a fast pace. So from A to B, velocity is increasing very fast. From O to A, of course this is increasing but at a lower pace. So this is how slope of a velocity time graph is interpreted. Now if someone asks you what is the acceleration, of course this will be known as average acceleration. What is acceleration from O to B? Then you have to write, because it is asking average acceleration between O to B. So we have to write velocity at B minus velocity at 0 upon the total time span, that will be TB minus 0, which comes out as VB upon TB. This is average acceleration for the entire journey. It has nothing to do with when it was increasing at a lower pace, when it was increasing at a higher pace. It is only interested in how much it changed from initial value to the final value. So this is how average acceleration is written. Here student, at this point student sometime make a mistake, and when writing average, never write as net slope is equal to, because of course average acceleration will be given by the slope. So slope never can be written as slope of first part plus slope of second part. So don't commit this kind of mistake. Never you can write net slope is equal to slope of part 1 plus slope of part 2. As someone may say that of course in this particular example you will get the same answer even if you add the slopes also, but this is not the correct method, because sometime you may get some result, you may get correct result, and sometime you may not. So never do this mistake. Slopes are never added like this. Always you have to write, when it is asking for the entire journey, you have to write acceleration as final velocity minus initial velocity upon the total time taken. This is how average term is calculated. Never do this mistake. I am saying this again and again. Slopes are not added as tan theta 1 plus tan theta 2 for the whole journey. Another case we can consider where velocity is drawn with time like this. Here, as you can see in the previous example, velocity with time was linearly increasing. Of course it was increasing, but that was linear. And here, as you can say, velocity is increasing with time, but this is not in some linear fashion. So here acceleration of course would not be uniform, because as you can see its slope is increasing with time, it's get on increasing. Here acceleration will not be constant. If graph of velocity versus time is non-linear, then acceleration is not constant. If it is linear, then acceleration is constant. Now let us see some more examples of graph. Again I am drawing velocity versus time. So many graphs are there. Let first graph be like this. Another be, this is all velocity versus time. Velocity versus time, the graph is like this. Then the graph is like this, and the graph is like this. All are velocity versus time graphs. Let us now interpret all of them. First graph is where velocity is increasing linearly with time. So this will represent, because velocity is increasing linearly, so acceleration, and you can see for the whole graph acceleration is constant. Acceleration is for the whole graph, slope is constant. Whatever be value of theta here, it will be the same here. So if slope is constant, of course acceleration will also be constant. So this graph depicts constant acceleration. Constant acceleration. Next come to the second graph. Here velocity, as you can say that with time it is remaining constant, its value is not changing. If it was 2 meter per second, it continues to be 2 meter per second throughout the journey. So if velocity is not changing, of course acceleration would remain 0. So this is, and slope also you can check by slope also. If mathematically you want to check, then just check out the slope. So slope here is 0, so acceleration would be 0. So this is 0 acceleration. Third motion you can depict. Third motion you can interpret. Here velocity is decreasing with time. It has started with some positive value and now its value is getting decreased to finally coming to 0. So this is decrement in velocity. Here acceleration would be, if you check at the slope, this also is negative. Here tan theta is negative. So this acceleration will be negative. Acceleration is negative. What does it mean, negative acceleration? This is retarding motion. So if acceleration is positive, it is called accelerating motion. If it is negative, it is called retarding motion. Now come to the last graph. Velocity is increasing but in opposite direction. So in this also acceleration would be negative, because acceleration is change in velocity upon time and velocity itself is negative. So acceleration is also negative, but it is not retarding. This is accelerating. So actually it is accelerating in negative direction. Acceleration is negative, but this is accelerating. Have you understood the difference between this and this graph? Here acceleration is negative, here also it is negative, but this is retarding motion because magnitude of velocity is getting decreased with time, whereas in second, magnitude of velocity is getting increased with time. Of course this is in negative direction, so acceleration is negative. Now we can draw distance time graph also with the help of these 4 velocity time graph. If velocity time graph is provided, of course you can draw the corresponding distance time graph. In first graph, as you can see, velocity is linear with time. So of course distance will not remain the linear. It will go on, velocity is getting increased. So slope, because now we are drawing s versus t, distance versus time. So slope will give you velocity and velocity has to be increasing. So how would it look like? Like this, where slope is getting increased with time. Next is where velocity is constant. If velocity is constant, slope of s versus t has to be constant, because as we had discussed earlier that slope of st graph gives you velocity. So if velocity is constant, slope has to be constant, and this will give you a straight line for position time graph. Come to the next part. Here velocity is decreasing with time. So if you write st, velocity is linear. So of course st graph will not be linear. Velocity is decreasing with time, so acceleration is negative. If it is negative, the graph will look like this. It will be a non-linear graph and it will look like this. It will be towards the negative. Now come to the third one. Here velocity is negative and it is linear also. So distance time graph will be non-linear but negative. In negative direction it is increasing. So it will be like in last graph, velocity is increasing but it is in negative direction. So position time graph also will be drawn in negative direction like this. So this is how distance time graph or position time graph can be interpreted with the help of velocity time graph. Now let us take one mathematical illustration so that we are able to solve all the kinematical terms mathematically. So one illustration I have taken. A particle is moving with a uniform acceleration. Its position at time t seconds is given in meter by the relation. The relation is given here, which is x is equal to, do remember we are studying only motion along a straight line. So motion cannot be one time in x direction and other time in y direction. It has to be completely in x or completely in y or in any other direction. So here it is given x is equal to 3 plus 4t plus 5t square. Now it is asking calculate the magnitude of its first, it is asking for initial velocity. Now as you know, I had just told you how is velocity written. It has to be dx by dt because it is asking initial velocity. So this is actually asking velocity at a particular instant, and whenever it asks for velocity at some instant, that is called instantaneous velocity. Instantaneous velocity is written as dx upon dt. So you have to differentiate the given term. Generally students get confused when to differentiate and when to integrate. So how would you decide? You have to check which physical quantity is provided and which one you have to calculate. So if position is provided and you have to calculate velocity, then go by the definition, because velocity is defined as differentiation of x. So of course you have to differentiate the term x. If it is the vice versa, velocity is provided and it is asking for x, then of course you have to integrate. Here x is given and you have to calculate velocity, so differentiate the term x. What it would be? This 3 is a constant, so differentiation will be 0. This is 4 plus 10t. This is a general term for velocity, but it is asking for initial velocity. So for initial velocity, t has to be 0. If t is 0, velocity at t is equal to 0 will be, substitute value of 0 here, so you will get 4 meter per second. It is given here that time is in second and distance in meter. So velocity, initial velocity or velocity at 0 time is 4 meter per second. Now come to the second part. It is asking for velocity at t is equal to 3 seconds. As we have calculated the instantaneous velocity, that is equal to 4 plus 10t. So just put the value of time and you will get velocity at that particular instant. So velocity at 3 seconds would be, substitute this value 3 here. This is 10, 3s are 30 plus 4, that is 34 meter per second. The third one is uniform acceleration. Now we have the velocity term. As you can see, velocity is a straight line function here. V is equal to 4 plus 10t. What kind of function this is? Straight line. So velocity is along a straight line. So velocity is varying as a straight line. If velocity is a straight line, velocity time graph is a straight line, acceleration has to be constant. And how is acceleration defined? It is equal to dv upon dt. So differentiate this, you will get the value 10 meter per second square. Now the last, position at t is equal to 5 seconds. This is asking position itself, and position is provided here in the given expression, which is x is equal to 3 plus 4t plus 5t square. Simply write the value t is equal to 5 and you will get position at 5 seconds. So x5 will be 3 plus 4 5s are 20 plus 5t square. So it will be 125. It comes out to be 148 meter. Here I had taken one very simple example and checked how the different kinematical terms can be calculated mathematically. Later in later sections we will solve a lot number of questions, so it will be very easy for you to solve a question if it comes from the kinematics. Now move to the next section. Let us first recall all the kinematical expressions just now we have learned. The first was velocity, that is ds by dt. Here, as we are studying motion in a straight line, so it is not of much importance whether we are putting vector sign or not. But in later chapters when we will come to 2D motion or 3D motion, this would be very necessary, right? So from now itself I am writing the vector equation. First is v is equal to ds by dt. This is actually definition of velocity itself. The next one is acceleration, that can be expressed as dv by dt. Now do remember, these two are the actual basic expressions only in kinematics. All other expressions are derived from these two expressions only. So definition of velocity and definition of acceleration will give you all the equations required to solve a kinematic numerical. So these two will be valid in all the conditions. So this is valid everywhere. In all the conditions it will be valid for all the cases. But if we consider, because a lot number of numericals you would get in which acceleration remains constant. So if acceleration remains constant, we can simplify these two relations in three very famous known kinematical expressions you all must be knowing. You have learned this from class 9th itself, and the expressions are, the first one is v is equal to u plus at. As just now I had said that I am writing the vector equation. I am writing the vector version of kinematical expression, though it is not needed much in this particular topic, but later it will be used. So from now on only I am using the vector notation. V is equal to u plus at. How would you get this from the above two expression? Because as I had said, these two are the only basic expression. The first one, v is equal to ds by dt, and a is equal to dv by dt. So now we will see how different expressions are derived from these two basic equations. I am starting with v is equal to u plus at. As you know, acceleration is dv by dt. So if acceleration is constant, take dt on this side and then it can be written like this. Now if you integrate both the sides, and since acceleration is constant, so it can be taken outside the integral, this will come out only integration of dt, and here this is integration of dv. Lower limit will be the initial velocity and the final velocity. Here for time, the lower I am saying the reference, it is starting from t is equal to 0 to some time t is equal to t. If you integrate this, you will get v minus u is equal to, acceleration being constant can be taken outside, and then it will be t. So now you got your relation v is equal to u plus at. Now let us move to the second equation. The second one is Again this is vector relation, S is equal to ut plus half at square. Here S is displacement term, not the distance. Students do a lot times this mistake that while calculating distance also they start using this formula, which is not correct. This can be used only if S is the symbol used for displacement. So it has to be used only for displacement relation, which is equal to ut plus half at square. Now how would this can be derived? As we know, V is equal to ds by dt. Take dt on other side. V dt is equal to integration of ds. Now here V cannot be taken outside the integral sign because this is not a constant. But of course, just now we have derived V is equal to u plus at. So instead of V, we can write u plus at and then integrate it. Of course, within the limits 0 to t. On left hand side, it will be for displacement or for position. If you take reference at the initial point, then initial will be 0 and final will be s. So if you now substitute the values after integrating, you will get ut plus half at square, that is equal to s. This is a vector relation as well. The last one is the third one, that is v square is equal to u square plus 2as. Now do you have any idea why I am deriving these relations? Because you all must be familiar with these relations. Still I am deriving it because in a number of numericals there may come a stage where the final formula will not be used. So you must know all the intermediate steps involved so that you can use that step to get the calculation. For this purpose only I am deriving the relations properly. The third one, as you can see, I have not put any vector sign here because third relation is actually a scalar or a projection form. So this is a scalar equation. It cannot be written in vector because as you all know, there is no square of vector term. Have you ever heard of square of velocity or square of acceleration? No. If you take its mod, then only it can be squared or cube. Otherwise, there is nothing like square or cube in vector algebra. So, if it is written square of some term, it has to be a scalar. Now how this will be derived? It has to be only along a single direction because I have not put any vector sign here, so it cannot be used directly for 2D or 3D motion. This is very important thing. Later you will recognize how important this is while discussing 2D motion, right? So from now only you have to know that this has to be written, always it is to be written in projection form. Now if you write this here, let us start with definition of acceleration. Acceleration can be written as dv upon dt. Here I am writing this in projection form. It is along a single direction, so no need to put vector sign above. A I have written as dv by dt. Can it be written as dv by ds into ds by dt? Of course this can be, because if velocity is not a function of time, if it is a function of s, then it cannot be differentiated with respect to time. It can be differentiated with respect to s, and then one ds by dt has to be multiplied. So a can be written as dv by ds into ds by dt. Now what is ds by dt? It is v itself. So this can be written as v dv upon ds. Now if you take ds on other side, then this will be a ds. Integration of this, that is equal to v dv. Of course you have to put the limits, initial velocity to final velocity, and on right hand side, as I have said, acceleration is constant, so this is only s variable here. If you write the original position as reference position, that can be taken as 0, then the integration limits will be from 0 to s. If you now integrate it and substitute the values, you will get your famous formula v square is equal to u square plus 2as. With this, our today's session is complete. In current session, we got familiar with all the kinematical terms and relation among them. In the next session, we are going to know about how these expressions are used in different physical situations. Also, we will know about a very interesting term, that is the relative motion. We will see what kind of motion is called relative motion and how the concept is applied to solve different kinds of numerical examples. Till then, please revise all the concepts we have learned today and then try practicing a good number of questions. For your preparation, it's a good luck. Goodbye.